In this video, we will talk about how to use Gauss-Jordan elimination. So here's the idea. If we have a system of equations, such as this system of equations right here, and we want to solve for x, y, and z, one way to do that is to place all of the values from the system of equation into an augmented matrix, and then use Gauss-Jordan elimination to convert this matrix into its reduced row echelon form, or RREF. And the benefit of doing so is that once a matrix is in this form, we can just see what x, y, and z are. So x is going to be equal to 3, y is going to be equal to 5, and z is going to be equal to -2. Now, there are 4 criteria that a matrix must meet to be considered in reduced row echelon form. The first is that all rows of zeros are at the bottom of the matrix. The second criteria is that each pivot entry is to the right of the pivot entries above it. So remember, a pivot entry is just the first non-zero value in a row. The third criteria is that all pivot entries are equal to 1, and the last criteria is that there are zeros above and below all pivot entries. So let's get into this example and see how we can actually use Gauss-Jordan elimination. All right, let's say we have the following system of equations and we want to solve for x, y, and z. The first step is we want to place all of these values in an augmented matrix. So here's how we do that. We write each of the coefficients of the x, y, and z values in a coefficient matrix, and then we write the values on the right-hand side of the equal sign in an augmented column. So here's what that looks like. 2, 4, -6, and then we create an augmented column where we write 38. And we can repeat that for the next 2 rows. So for this x right here, imagine this is a coefficient of 1. So we'll write 1, 2, 3, 7, and the last row will be 3, -4, 4, and -19. So that's the first step. Next, we want to convert this matrix into reduced row echelon form. So ideally, at the end of it, this value in the top left corner right here is going to be a 1. So notice that the first step that we could do is we could just swap row 1 and row 2 so that this 1 is moved into this position right here. And that's a perfectly valid elementary row operation. We're allowed to swap rows. So let's do that. Let's say our first step is row 1 is going to be swapped with row 2. So here's what that looks like. We get 1, 2, 3, 7, 2, 4, -6, 38, and then the last row remains unchanged. Okay, so our first pivot entry is going to be the first non-zero value in the first row. So that's this 1 right here. Remember, we want to make all zeros below and above the pivot entries. So we want to convert this 2 to a 0, and we want to convert this 3 to a 0. So how could we do that? Well, we could start by saying, let's just take row 2, right here, this 2, and subtract 2 times row 1, because we would have 2 minus 2, and that would make this a 0. So if we do that, let's say row 2 is going to become row 2 minus 2 times row 1. So here's what that looks like. The first row doesn't change at all, so we'll just rewrite that. And the last row won't change at all either, so we can just rewrite that. Now, this second row, we said is going to be 2 minus 2 times 1. So 2 times 1 is 2, so 2 minus 2 is 0. Next, we get 4 minus 2 times 2. So 2 times 2 is 4, so we get 4 minus 4, that's 0. And then we get -6 minus 2 times 3. So 2 times 3 is 6. So -6 minus 6 is -12. And then lastly, we get 38 minus 2 times 7. 2 times 7 is 14, so 38 minus 14 is 24. All right, so let's make a little room and rewrite this matrix over here. Okay, next we want to make this 3 into a 0. So how can we do that? Well, notice if we do 3 minus 3 times row 1, we would have 3 minus 3, which would make this a 0. So let's do that. Let's say row 3 is going to become row 3 minus 3 times row 1. So here's what we get. The first row doesn't change, so we'll go ahead and rewrite that. The second row doesn't change either. Now this third row, we have 3 minus 3 times 1, so that's 0. Next, we have -4 minus 3 times 2. So 3 times 2 is 6. So -4 minus 6 is -10. Then we have 4 minus 3 times 3. 3 times 3 is 9, so 4 minus 9, that's negative 5. And lastly, we have negative 19 minus 3 times 7. 3 times 7 is 21, so negative 19 minus 21, that's negative 40. So recall that we said we want each pivot entry to be a 1. Well, notice if we divided this negative 10 by negative 10, that would automatically become a 1. And after that, we could switch these two rows so that we have a 1 right here and a 0 directly below it. So let's go ahead and do that. So let's say the new row 3 is just going to be row 3 divided by 10. So here's what that looks like. So the first row doesn't change at all. Neither does the second row. Row 3 is row 3 divided by 10. So 0 divided by 10 is just 0. Negative 10, excuse me, this should be a negative 10. Negative 10 divided by negative 10 is 1. Negative 5 divided by negative 10 is negative 5 over 10, or 1/2. And negative 40 divided by negative 10 is 4. Okay, so next we said, let's go ahead and switch row 2 and row 3 so that we have a 1 right here, which will be our pivot entry in row 2, and we'll automatically have a 0 below it. So let's swap row 2 and row 3. So we get row 1 doesn't change at all, so we'll just rewrite that. And then we have 0, 1, 1/2, 4, and 0, 0, negative 12, 24. Okay, so let's go ahead and rewrite this matrix over here and make some room. All right, so notice that here's our pivot entry in row 1, here's our pivot entry in row 2, and here's our current pivot entry in row 3. We said that to be in a reduced row echelon form, all of the pivot entries need to be equal to 1. So how can we make this a 1? Well, we could just divide by negative 12. So let's do that. So let's say row 3 is going to become row 3 divided by negative 12. So here's what that looks like. The first row doesn't change. The second row doesn't change. And then the third row, we have 0 divided by 12 is 0. 0 divided by, negative 12. 0 divided by negative 12 is 0. Negative 12 divided by negative 12 is 1. And 24 divided by negative 12 is negative 2. Okay, so each of the pivot entries is equal to 1. Now what we can do is, working from right to left, we need to convert each of the values above the pivot entries to be 0. So in other words, we want this to be 0, this to be 0, and this to be 0. So how can we do that? Well, notice if we take row 2, so this 1/2 right here, and we subtract 1/2 of row 3, we would get 1/2 minus 1/2. That would make this a 0. And then notice that to make this 3 a 0, we could do row 1 minus 3 times row 3. So we can do both of these operations at once. So let's say row 1 is going to become row 1 minus 3 times row 3. And we just said that row 2 is going to become row 2 minus 1/2 of row 3. So here's what this looks like. So our last row doesn't change, so let's go ahead and rewrite that. Okay, row 1 is row 1 minus 3 times row 3. So we get 1 minus 3 times 0, that stays a 1. Then we get 2 minus 3 times 0, that stays a 2. And then we get 3 minus 3 times 1. So 3 minus 3, that's 0. And then we get 7 minus 3 times negative 2. So 3 times negative 2 is negative 6. So we have 7 minus a negative 6, which is 7 plus 6, which is 13. Now in row 2, we said we're going to do row 2 minus 1/2 of row 3. So 0 minus 1/2 of 0 is 0. 1 minus 1/2 of 0 is 1. So these aren't changing. Now we have 1/2 minus 1/2 of 1. So half of 1 is just half. So we have 1/2 minus 1/2, which is 0. And then lastly, we have 4 minus half of negative 2. So half of negative 2 is negative 1. So we have 4 minus a negative 1, which is 4 plus 1, which is 5. Okay, now notice we only have one more step left. We have to get this 2 to be a 0. So how could we do that? Well, if we just say row 1 minus 2 times row 2, we would have 2 minus 2, which is 0. So let's do that. So row 1 is going to become row 1 minus 2 times row 2. And here's what that looks like. So we have, let's go ahead and rewrite the last 2 rows since those aren't changing at all. So we have 1 minus 2 times 0, that's just a 1. 2 minus 2 times 1 is 0. 0 minus 2 times 0 is just 0. And then we have 13 minus 2 times row 2. So 2 times 5 is 10. So we get 13 minus 10. That's a 3. Okay. So this is in reduced row echelon form. And notice that this represents the x, this represents the y, and this represents a z. So we can see that x is 3, y is 5, and z is 2. So let's rewrite that over here. Okay, so we said our final answers were x is equal to 3, y is equal to 5, and z is equal to negative 2. So these are the final answers. Now, if we'd like to check our answer, we can plug these values into one of the original equations. So if you'll recall, here's what our original system of linear equations looked like. Let's just pick one of these and see if these values actually work. So for example, let's pick this first equation. We have 2 times x, so x we said is 3, plus 4 times y we said was 5, minus 6 times z we said was negative 2, is equal to 38. Let's see if this left-hand side is actually equal to 38. So 2 times 3 is 6, plus 4 times 5 is 20, minus 6 times negative 2 is negative 12, so minus a negative 12, that's plus 12. Is this equal to 38? So we get 6 plus 20 is 26, plus 12, 26 plus 12, that is equal to 38. So that checks out. So that's just a way to double check that we got the right answers for x, y, and z.